So here's week 4 notes, test Thursday 10-3. We're going to study the periodic table. So these are some things you have to know from the periodic table. Alkali, metals, alkaline, metals, and then hydrogen, it's its own family. So these are families because they act the same. So there's somewhat of a assumption that everything and people in a family will act the same. Then we have transition metals. We have halogen or noble gases. We have halogens. And then we have the semi-metals or metalloids. And that is it for naming metals here and here, or naming the families. Places where I put X's, you don't have to know the families. So now we have to know the group numbers. First we have 1 through 18. You can see me counting, and then the noble gases are 18. Alkali are group 1, alkaline group 2, and so forth. And then we have 1A through 8A. Sometimes those will be written like Roman numerals, but in class I just wrote the number. It's just a matter of being able to reference different families and so forth. And we have periods 1 through 7. Periods are cross. Sometimes I like to write them on the right because it's like a sentence. And one other thing is the diatomics. Diatomics I'll circle in red. And so there's 7 of them. And so you have to be able to identify the diatomics. So something that is going to come up in week 5 are the metals, non-metals. So I might as well introduce them to you now. We have the semi-metals here, which act like both metals and non-metals. So let's do the non-metals. The non-metals are to the right of the semi-metals. So we got 5, 4, 3, 2, and then 1, and then I guess that's going to be a non-metal as well, and then helium as well, and then hydrogen as well. So these are the non-metals. To the right of the semi-metals. And then we have the metals, which is to the left of the semi-metals. Down here, don't worry about those. And then lanthanides, actinides, we're not worrying about those either. So on the left of the metalloids or semi-metals are the metals. To the right are the non-metals. And here you can see what I am saying and the names and so forth. You do have these labeled as what? Non-metals, but they're not stable, and but again, you can they're not going to be asked. So this is from your periodic table. We know the top number is protons and electrons, where electrons can change. We're going to ignore that bottom number for now. Protons are sometimes referred to as the Z number, but I only taught that for Alex. Now, the mass of a element is protons plus neutrons. Keep in mind, I write that charge up at the top right because that is the charge of the compound. So protons plus neutrons equals mass. Also, that 9 is the atomic number. So the atomic number is equal to protons. That atomic number cannot change. You cannot change the element itself by adding or subtracting a proton. So here is the determination of protons, electrons, and neutrons. We did quite a few of these in class. So I'm just going to do one, and really if you know how to do one and you're confident about that, the rest are going to be pretty easy. The second last one is molybdenum. Molybdenum. That is element 42. It means atomic number is 42, protons is 42, electrons is 42. Mass is protons plus neutrons, so that's 96. Then hyphen notation, molybdenum 56. Isotope notation, mass at the top, protons at the bottom, and then MO. So that is how you do all of them. So rewatch that if you don't know how to do and try some of these up here. But the same process is for all of them. So keep in mind, these right here cannot be done because we're not giving enough information to determine mass number. Top one we can do, hydrogen, we got H, mass number 1, atomic number 1, protons 1, neutrons 0, electrons 1, and then we have 11H. The next thing we're going to look at is ion charges. So electrons can be gained or lost in an atom and will form ion charges. Protons do not change, neutrons can, but right now we're just looking at electrons. So alkali plus 1, alkaline plus 2, then group 13 plus 3, then 0, minus 1, minus 2, minus 3, and then zinc plus 2, and silver plus 1. Now, we're going to discuss what this means in the next slide, but we're also going to look at outermost electrons, and those are valence electrons. So halogen or alkali, 1, 2, we're skipping the middle ones. The transition metals can form various charges that we'll learn about soon, but plus 3, nope, that has 3 valence electrons, not plus. So we got 3, 4, 5, 6, 7, 8, with helium having 2. Now, electrons can be lost or gained because everything wants 8. So you are full after you ate something. And so if something gets 8 or 2, hydrogen wants 2, then it's full and will no longer react. So for example, halogens have 7 valence electrons, forms a -1 charge to get 8 valence electrons. Let's write out an example. Oxygen, if we looked on the last periodic table, forms a -2 charge. So oxygen has 6 valence electrons. It gains 2 electrons and it forms a -2 charge. Getting something negative will make you negative. Now magnesium will lose 2 electrons, and because it wants to form -2 charge, because underneath it has 2 valence electrons, underneath that 2 valence electrons we have a full 8 valence electron shell. So I'll write out the examples here. Oxygen, I'll do 1 because it's the same thought process. Oxygen here, atomic number is 8. Protons plus neutrons equals mass. So neutrons has to be 8. And electrons is 10. Therefore, oxygen forms a -2 charge, just like we did in the last slide. More where neutrons and protons do not equal each other. Aluminum is element 13, protons 13, neutrons 14, because mass minus protons is 14, 27 minus 13 is 14. Now we have electrons, 3, therefore aluminum forms a +3 charge, which matches what you saw on the periodic table in group 3A or 13. Keep in mind, a cation is positive, so like magnesium 2+ that we've been doing is a positive, oxygen is a negative. Now, I don't care how you write that positive or negative. You write it like this, or Alex Wildo. So that first one is the correct way. So hydrogen is its own family. Here's hydrogen trying to disguise itself as an alkali metal or group 1 metal, and I don't think the cat is buying it. So we explained this earlier, that everything wants 8 valence electrons. So potassium, for example, has 1 valence electrons, but it forms a +1 charge. And you're going to see that underneath a potassium, one element is 8 more electrons. So if it loses one valence electron, if it loses one, then it has 8 underneath. Here is, we'll do one Alex. Oxygen is in period 1, 2, group 6A or 16. Now, these here, again, practice on Alex. I'll do one of these here. Magnesium is in group 2, or the alkaline metals. Therefore, we know that it's Mg2+, that's a cation. Now these will form the ion that we spoke about. So here iodine goes in group 7 valence electrons, practice on Alex. One thing we're going to talk, or we've talked briefly about, is electrons are negative, thus want to be as close to the center as positive. So here, these are attracted to each other like magnets. They want to be close to each other as possible. That leads to electron configurations. And I'm just going to start off and I'll explain it more later. 1s, 2p, 3d. Now, if I were to pick an element, so right there, that's zirconium. What is the electron configuration of that element? It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 1, 2, 3, 4, 5s2, 4d2. So keep in mind how I did that is I just wrote 1s, 2p, 3d, and then if we write down, this is 2s, 3s, 4s, 5s, 3d, 4d, 5d, 2p, 3p, 4p, 5p, 6p. Now, and then we just read it like a book. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d2. So the way that you can rewrite this later is put them in order of the front number. Let's do 2s2, 2p6. Nope. For D2, 5s2. And you're going to learn this later, that those are the valence electrons. So that's in 5. The front number is 5, therefore it's further away. And we're going to cover that more. Some more electron configurations, and if this doesn't make sense, then there are a lot of resources online, and then there's ALEKS. So if I were to circle this element right here, we know that it's going to end in 3p1, 2, 3, 4. So it's going to go up to 3p4. Now, if I were to circle another element, let's say, whoop, I messed up with that one right there, 1s2, 2p, 3d. If I were to circle this element here, D's are 10 across, so 10, 9, 8. That's going to end in 3d8. If I were to circle an element here, 2s, 3s, 4s, 5s, 6s, that's going to end in 6s2. Now I'll do another one for practice. Otherwise, practice them on ALEKS. If I were to circle this one right here, it's going to be 1s2, 2s2. So we're reading like a book. 2p6, 3s, 3s2, 3p6, 4s2. I don't even remember what I circled. Oh yeah, that's it. 4s2. And here we have it written also in order of front number, and that those are the valence electrons, 4s2, and that makes sense because these have 2 valence electrons. Shows just the way that can be written at the bottom. And here, this element, and lanthanum, has 2 valence electrons. That's why we would write them in order. 6 means furthest away, which we'll do some of later. Will not be tested on electron configuration exceptions, so just do it like normal. This is ALEKS, practice ALEKS, pretty easy here. ALEKS again, pretty easy. ALEKS again, notice it's neutral atom, it's not the ion of beryllium. Beryllium forms a +1 and +2, yeah, +2, so notice it's a neutral atom. Electron configuration of zinc. So I will skip that and you can look it up. Keep in mind, I think no, zinc is not a exception. So you can look at that configuration, ends in 3d10. Again, there's other ways to learn this. 1s, 2s, 3s, 2d, 3d, and so look that up if this is not making sense and you draw arrows like that. Well, gas configuration, or shorthand notations or whatever, or abbreviated notation. So now let's do some examples. This is calcium. Normally it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And these are annoying. So I'm going to look for the last noble gas. Keep in mind helium is a 1s2, and then all the rest are 2p6, 3p6, 4p6, and then we can write that wherever the last noble gas is, 3p6, which is argon, So this is argon in brackets, and we just have to write 4s2. And so this is the abbreviated notation for calcium. Now, calcium has 2 valence electrons, which makes sense. The largest front number is 2. Here is what is this? 4, 1, 2, 3, 4. So this is carbon. Carbon has 4 valence electrons, 1, 2, and that makes sense. Helium is 1 before it, and the rest of those you can finish. Neon here, this is 5 valence electrons because the principle of the front number has 5, and this is going to be neon, 1, 2, 3, 4. So this is phosphorus, and phosphorus, if you count valence electrons, is 5. So here we can look at argon, AR parentheses, and then we got 4s2, 3d 1, 2, 3, 4, 5, 6, 3d6, or a better way to write it, although you wouldn't be taken off, is 3d6, 4s2. Now that element has 2 valence electrons because 4 is the furthest away, and those 2 electrons there would be the valence. There's more, Alex, you can practice. S blocks, P blocks, D blocks, you can practice. More of that. Now, important, electrons are negative, thus we want to be close to the center as possible. Thus, we'll move in a certain way to make this happen. Now, you don't have to look at this, although it'll probably help based on what we're going to start with in week 5. So we're going to learn the periodic trends now. Now, a lot of times teachers just give this chart to have students memorize it, but that's very tough. I honestly only know one periodic trend, and then I relate the other periodic trends to it. So if you look at the periodic table, francium is down here. Francium is the largest, and then fluorine and helium, I'm going to use both of those. Whenever I say fluorine, I'm going to say both is the smallest. Therefore, we know as we go down, we get larger, and as we go to the left, we get larger, because the closer it is to francium, the larger it is. And I remember that because Fr is 2 letters, F is 1 letter, therefore francium is larger than fluorine. Fr, largest, fluorine, helium, smallest. So ionization energy is the energy to remove 1 electron. So let's do an example. So francium wants to form a +1 charge because it's in group 1, and so the energy it takes to do this. Now it wants to form a +1 charge, so it probably won't take a lot of energy, but the way to think about this is, now francium is the largest, now helium is the smallest, and we know that we have protons and electrons, protons in the middle and electrons on the outside. So if you're at a Taylor Swift concert and you are the negative charge and Taylor Swift is the positive charge, and here, what is going to take more energy to get you to leave the concert? Now, if you're further away, it will take less energy. Thus, ionization energy, the amount of energy to remove an electron, is correlated to the radius, but it's oppositely correlated. So here, this is going to have the less or least amount of ionization energy, because it doesn't take a lot of energy to remove that electron because it's furthest apart from the proton. So protons and electrons are like magnets. The further you are, the less attraction. Now helium, or fluorine is going to have the highest. And therefore, and that's because the electrons and the protons are the closest. Magnetic charge, or you got front row seats to Taylor Swift, which probably costs as much as a year at school, but you're not going to leave that concert no matter what, somebody says to you. Is that relevant? So fluorine wants to form a -1 charge. So it really is not going to lose an electron. Fluorine wants to form, it's a halogen. At 7, it wants 8, because if it 8 something, it'll be full. Or if an 8 electron, it'll be full. And therefore, it's not going to want to lose another electron. As we know, fluorine wants to form a -1 charge because it has 7 valence electrons. And it will form fluorine ion, which has 8. Forms an ion, the radius changes dramatically. So we said fluorine or francium is the largest, and helium and fluorine are the smallest. But if it loses an electron, so like francium wants to lose an electron, it's losing something, it's going to become much smaller on an exponential scale. Just like if fluorine gains an electron, it is going to become much larger. And that is just because the magnet in itself, and something we'll talk about later, will be less strong, and based on the protons in the middle, but we'll talk about that later. Now, electronegativity is different. It's pulled on shared electrons in a chemical bond. Now, here, let's think about it. We have francium, largest, fluorine, smallest. And there's electrons right there. That fluorine has a positive charge in the middle, so does that francium. Now, since it's based on radius, the protons in fluorine are closer to those electrons. Therefore, that fluorine is going to pull those electrons more. Now, this is, again, based on radius size and based on relevancy, based on what francium and fluorine, the ions it wants to form. However, helium has the lowest ionization energy. For all the other trends, or electronegativity, for all the other trends, it follows the same thing. But I've been using fluorine equals helium for a reason. Helium already has 2 valence electrons, or neon already has 8 valence electrons. So it's not going to pull any electrons because it doesn't need any more. So helium and neon are going to have the lowest electronegativity because it is already full. Now this is relevant based on the ion charges, because again, if let's say we have sodium and fluorine, 2 electrons, sodium wants to form a +1 charge and fluorine wants to form a -1 charge. So electronegativity is the pull of those electrons. Fluorine's stronger at pulling those electrons. So eventually, fluorine just takes them. And there'll be nothing shared in the middle. So I should not have those overlap. And then there's an attraction between them. So just like NaCl, what does NaCl form? Because chlorine pulls an electron from sodium, and then positive and negative attract. Now, something I should say here, we still got to do these notes tomorrow, is remember when chlorine gains an electron, it becomes much bigger. And when sodium loses an electron, it becomes much smaller. So this would be a better representation of that. So let's just do an Alex. We're going to follow the trend. Now, remember when it gains an electron, it becomes larger. Well, let's do the first trend there. The closer it is to helium and francium, or helium and fluorine, the smaller it is. So we have neon, which is right there. So atoms in order of decreasing size. So we know that neon is going to be the smallest. And then beryllium is way on the opposite side, and carbon is in the middle. So we have beryllium as the largest, then carbon, then neon. So if you look at which one is closer to francium, francium, remember, is the largest, and fluorine, helium, is the smallest. So now if we do a one with an ion, if it loses an electron, then it becomes quite a bit smaller. So the smallest here is going to be sodium plus, and then we got sodium, Na, and potassium. Potassium is closer to francium, so then potassium is going to be larger. So that's wrong. In order of order of decreasing size. So sodium is the smallest, or sodium ion is the smallest, and then potassium is closer to francium, so that's the largest, then Na, then Na plus. And so these are on Alex and a good way to practice them. And obviously if you lose, or if you gain 2 electrons, you're going to become quite a bit larger. And ionization energy, the energy it takes to remove an electron. For here, fluorine and helium is the largest, and so the closer that it is, and then francium is the smallest, the closer it is to fluorine and helium, the higher the ionization energy. So we got potassium, looking at the periodic table, potassium, rubidium, magnesium, sodium. So the ionization energy for potassium, for rubidium, is going to be the smallest. And then we have what potassium is next. And then we have sodium is next. Oh no, I should have 4, 3, 2, and magnesium is the closest to fluorine helium, and therefore that is going to have the highest ionization energy. So I don't know if I wrote those how Alex does them, but essentially magnesium is highest, and rubidium is the lowest, because remember what I said about those two. That is the week 4 notes. Week 5 correlates quite a bit to week 4, but it's going to take some work to completely understand them.